how to do conversion, all right, from decimal to binary, okay, from binary to decimal, and then from hex to decimal, okay, and decimals to hex, and also from hex to binary, okay, and binary to hex as well. Okay, so we look further a little bit, just couple of quick revision, okay, uh, on the conversion of hex to binary. Okay, so hex to binary is actually pretty simple. Okay, so you just need to remember that each 4 bit, okay, each 4 bit of that binary number is only consisting up to 0 to 15, right? Meaning that it is a 16 bit. Okay, if you look here, okay, so 2, so it's actually 0010 because for the first, okay, okay, so here it is equivalent to 8. All right, here is 4, here is 2, okay, so here is 1. Okay, so it is 15, right? It is 15, 0 to 15, so it is 16 bit. Okay, okay, so you have 9, so 9, 8 and 1, right? So B is, as you learned before, it is 11. Okay, 11, I mean 8, okay, 8, 2 and 1, right? So 8, 2 and 1, so this one. Okay, any questions so far? Okay, in order to do the conversion of the decimal, uh, so this decimal to hex, okay, so decimal to hex, as we learned on Monday, okay, so we need to perform the conversion into binary first, okay, conversion into binary, and then binary back, okay, back to the decimal. Okay, so in order to know the decimal one from the binary, okay, meaning that base 2, okay, so you just look at the what is the most significant bit, okay, that has the 1 value. Okay, for example, here it is up to the 1 0 1 2 3 4 5 6 7 8 9 10, so 2 to 10, right? So 2 to 10 is 1 0 to 4. Okay, and then you just add whatever one that you have, then you add, you sum all of that, then you will get the answer in terms of decimal. Okay, all right, so you just convert to binary first, and then convert that binary to hex, if, right, if it is from decimal, okay, from decimal back to binary, okay, and then binary to hex if you want to convert from decimal to hex. Okay, so you know that on how to convert from decimal to binary. So if you cannot remember, so just just flip back into our previous slides, so you can look for the example. Okay, so we have, okay, we have the relationship, okay, from here it's shown that from 0 to 31, all right, so this is for the binary bit of 5. Okay, so from 0000 to 1111. Okay, so you see how different is that, okay, in terms of hex numbering. Okay, after F, it's come back to 1 0. Okay, after F, it's come back to 1 0, and then it follows with 1F. Okay, what is after that? Okay, so it becomes 2 0. Okay, and then to 1 to 2 to 3 to 4 5 7 to 9, and then comes to 2A, to B, to C, to D, and then to F. Okay, after 2F, it comes to 3 0. Okay, so that's how the increment of hex numbering. Okay, we look into the addition of 2 bits. Okay, if A and B is binary, if A and B is binary, then if both are 0, then you have carry and sum. So both of that are 0. Okay, so it is like, so if A 0 and B 0, so you have this is carry, so this is carry, and this is sum. Okay, if both are ones, then you have both carry and sum as, sorry, 1 1, it become 1 0. Okay, so this is how you perform the addition of binary numbers. Okay, and then all right, so that's 1 and 1. Okay, so sometimes you will get, okay, you will get 1 and 1 when you have additional 1 from here, then you get 1 and 1. All right, so that's the maximum of what you have for both carry and sum. Okay, let's have a look here for this number. When we do the addition of binary, okay, 1 1 is becomes 1 0. Okay, so is 0 here, okay, and then you carry 1 over there, and then 1 plus 0 plus 0 is 1. Okay, and 1 plus 0 is 1. 1 plus 1 is 1 0. Okay, so you obtain this one. Okay, you want to know what is the decimal equivalent. Okay, this is can directly be converted to the decimal, because you know this is 2. Okay, this is 4. Okay, this is 16. All right, so 16 plus 6, it is 22. So that's correct for your decimal equivalent. Okay, or you can do conversion of that first. All right, so that's become 13, and then this becomes 9, and then just add both of that numbers, so you also obtain 22. Okay, the problem is when you want to perform the subtraction. Okay, the computers that we learn, okay, have an adder circuit. Okay, as you learn in the electronics. Okay, you have half adder, full adder. All right, so you can do the addition. Okay, always you can do the addition without problem. But whenever it involves the subtractions, it becomes problem, because the computer doesn't know how to perform the subtraction. So the way the computer can perform the subtraction is also by doing the addition as well. But the way we do that is by working on the 2's complement. Okay, so this is always the way, okay, to perform the subtraction using the computer. Okay, so it's not like a mathematics, a straight mathematics, where you can just okay, minus x and y. All right, but you need to have the 2's complement. There will be 1's complement and then 2's complement to complete that. Okay, so how it works. Okay, so here how you want to do that. Okay, let's say you have the binary number. Okay, 1's complement is actually inversion. All right, So you have inverter gates, right, in the computer. So it can invert your 1 to 0 or 0 back to 1. Okay, so here is what we have in the computer, ones complement. So it inverts the bit first. Okay, ones becomes 0 and 0 becomes 1. So let's say this is your number. Okay, 100111101, and then when it is inverted, so it is the first complement, sorry, it is a ones complement. Okay, so 1 becomes 0 and 0 becomes 1, so it becomes 011000010. Okay, so that's your ones complement. All right, to get the second complement, you just add 1. Okay, you just add 1 then you get the result. Okay, so 0 plus 1, so 1. Okay, and then this becomes 1 0, and it just follows that. Right, so this is your 2's complements. Okay, all right, so if the results, okay, is less than 16, okay, write the digit as the sum for that position. Okay, so let's say if you see that okay, so this is the way how do you do the 2's complement. Okay, so you get the result of that. Okay, so this is for binary. Okay, so for hex, okay, so how do you perform the subtraction for the hex? Okay, for the hex, okay, for example, I have a number here. Okay, this is your hex number. Okay, so what you have here, 9, okay, and E. All right, so you need to borrow. Okay, you need to borrow because E is greater than 9. So here E is equivalent to 14. All right, equivalent to 14. So D, you must um, take 1 from D, so it becomes C. Right, okay, and then so here this digit 9 must be added. Okay, must be added with 16. Okay, must be added with 16. Okay, so what do you have? Okay, what do you have here when we add 16, okay, to this one? Oh, sorry, again, this is for addition. Okay, this is not subtraction, this is addition. Okay, so I need to erase back, sorry about that. Okay, okay, so addition is okay. Okay, addition, if it is greater than 16, okay, okay, so 9 plus E. So 9 plus E, E is, so E is 14, all right? Sorry, E, yes, E is 14, okay, and 9, 14, you plus 9, you obtain 23, okay? But here, you cannot write 23, okay? Because for the hex numbering, it is from 0 to F. Your F is 15, okay? So you need to minus this 23 with 16, so you obtain 7. So you can carry 1 over there. Okay, so it becomes 7 over here. Okay, so what you have, then you have D plus 1, okay, D and E. All right, so it becomes E. Okay, and then plus B. So what do you have? Okay, so you need to convert that, all right, into the numbering. So D becomes 13, and then B is 11, right? And then you plus 1. So 14, so here 3, 4, 5, okay, 5 and 25. Okay, as this one as well, okay, so you need to minus, you need to minus back with 16. Alright, 25 you need to minus with 16, so you obtain 9. So you put 9 over there. Okay, so once you put 9 over there, then you also carry 1, right, over there. Okay, you have 7, 8. So 8 now is okay because it's less than 16. And then 2 plus 9, it is 11. So it is B. So this is the results for the addition of the hex number. Okay, any questions so far?
Doctor,
Yes?
so if we have the carry, we have to add 1 above the
Yes.
number.
Yes. But you need to know that that 1, okay, in terms of hex. Okay. So meaning
Okay.
that if it is greater than 16, okay, meaning that if the results is 16, mean that what you need to put down there is 0. Okay.
Okay.
Is 15, then you just put F. Okay, because F is the greatest number for the hex. Okay, all right. Take a break for 1 to 2 minutes. Okay, any other question? All right, if not, then we continue. Okay, now it becomes to the subtraction. Okay. Um, okay, there is no. Okay, let's do the other way around. Okay. Okay, you know this is the results, right? Okay, let's say take this one. Okay, minus with that one. Okay, so you have B8 line 7. Okay, and you have, let's say, I take this one, 94 BE. Okay, you cannot subtract 7 from E, right? So you need to borrow. Okay, so 9 becomes 8. Okay, and then 7 you need to add with 16. Okay, so what is that? 23. All right, 23, you need to minus E. The E is 14. So you get 9, right? Okay, so Now 8 minus B cannot do as well. So you need to borrow. So this becomes 7. Okay. So 16 must be added to 8. So you have 24 minus B. So B is 11. Alright. So what you have is 13. So 13 is equivalent to D. Okay, any question?
No.
Okay, so here 7 minus 4. So it's okay. So you get 3. And then B is 11 minus 9. So you get 2. Okay, so you get the same answer. 2, 3, D9. Okay, so that's how you perform the subtraction. Okay. Alright, in this learning the computer, you also need to learn about the ASCII. Alright, ASCII code or ASCII number. Okay, ASCII is what is used in your keyboard. So that's why your keyboard is called as ASCII keyboard. Okay, because it is designed according to the ASCII numbering. Okay, so what is that? Okay, um, so because the information in the computer is always working based on 1 and 0, as I mentioned before. So you have only signal, right? One, like your switch. Okay, your switch on the in your room. Okay, so you turn off and on, off and on. So it just work like that. Okay, but there are so many circuit, so many switching circuit. All right. So it works very fast. Okay, it's less than one so it's less than 1 nanosecond. Okay, less than that because it's 1 to minus 10 to the minus 12. Okay, so we must assign, okay, because it's still so you must assign these binary numbers into the letters and characters. So for us to make it easy, right, to write. Okay, so if now, like say if you are still working on 0 and 1, so we need to type on the keyboard is 0101. All right, so that's the problem. Okay, so so we have a new code names called ASCII. So American Standard Code for Information Interchange. Okay, so that's the uh, full term of that. Okay, so it assigns binary patterns for number 0 to 9, okay, and all English alphabet letters, all right, for the upper and lower case. Okay, so like our normal alphabet, so we have numbers and also we have alphabets. Okay, and also we have codes, control, and punctuation marks. Okay, so this is the equivalent of hex numbering to this symbol. Okay, so you look over here. Okay, ASCII use a total of 7 bits to represent each code. Okay, why it is 7? Okay, because as you can see that, okay, what is the meaning of that? So this is the bit, right? This is the bit. Okay, this is the bit. So this is 8-bit, right? So in terms of binary, so it use up to this. All right. So it's not using the 8th bit. Okay. So here is used up to that. Okay, meaning that the most number that is covered over here is this is 1 to 4. All right, so mean that it is 7. Okay, you look that is up to 7. Okay, you get it? Okay, so this is for the first bit. Okay, so the maximum number is 7 and the maximum code is F. Okay, that's for the ASCII number, ASCII code. Okay, it used 7 bits. Okay, to represent, okay, each of the code. Okay, so you look that from 41 Okay, starts from the symbol A, the capital A, okay, until 7A. So we have the small z. Okay, so complete codes you can check on the book, okay, or you can Google on the internet, so you can find how this hex number is assigned to the symbol of the ASCII. Okay, so ASCII is the standard that we use right now. Okay, the standards for keyboards and provide the standard for printing, okay, and also displaying characters, okay, by the output devices. Okay, so the pattern of ASCII was designed to allow for easy manipulation of the ASCII data. Okay, so as I mentioned before, so digits for digits 0 to 9 is represented by ASCII code of 30 to 39. As you see here, it is for the alphabet, right? For 44 below that, okay, below that is used by the digits. Okay. Alright, this enables a program to convert ASCII to decimal, okay, by masking off. Okay, masking off means so we close, alright, we close, so it's masking, okay, changing to 0 the 3 in the upper nibble. Okay, let's say, so we have 3 1, okay, so we must 3, so we must this one, so we don't see 3, right? Okay, so it is equivalent to digit 1. Okay, also for other digits as well. Okay, so this is the meaning of masking the 3. So upper nibble, this is the nibble. Okay, so that's the meaning of nibble. Okay, nibble is equivalent to 4 bits. Okay, one nibble equivalent to 4 bits. Okay, so this is a nibble. Okay, one is a nibble. Okay, 3 is also a nibble. Okay, but one is called as lower nibble. Okay, 3 is the upper nibble. Okay, so nibble is equivalent to 4 bit. Okay, okay, so this is one nibble and then this is another nibble. Okay, so conversion of between uppercase and lowercase is as simple as changing bit 5 of the ASCII code. Okay, so as you can see here, all right, so it is changing, okay, of bit 5. Okay, bit 5 of the ASCII code. So bit 5 is here, right? 4 5. So when there is change over here, okay, meaning that uh, this one there is a change. Okay, if there is a change in the bit 5, then there is a change in the uppercase and lowercase, as you can see here. So we have change, right? We have a change, okay, from 5, okay, and then it's become 6. All right, when it becomes a 6, then there is a change of the bit. Okay, all right, so that's the beauty of the ASCII code. All right, so we don't wait until 5F. Okay, as you can see that it's changed directly, okay, from the capital Z, okay, to a small a, okay. We just change the upper nibble of that. Okay, toggle one nibble into 5 to 6, okay, then it becomes a small letter. Okay, this is the other codes of the ASCII. All right, so you can observe there, okay, how it is used. Okay, except 0 0, okay, it's not used. Okay, it comes from 0 1, okay, until the 7F. Okay, as he said, because he used the first 7 bits. Okay, he used the 7 bits of the of the binary. Okay, so he used 7 bits so to write the ASCII code. Okay, So others below than this digit, so it is for the symbols. Okay. Okay, this is what I just mentioned. All right. So you need to also know that about the signal. Whenever we have a signal 0, okay, or is less than 1, or just between 0 point something, then we consider that as 0. And if it's above than 3, then we consider that is as 1, right? Okay, so this is the switching methodology, all right, as I mentioned. Okay, so in the computer, so we have the logic gates, all right? So because it's combination, okay? What we want to do, if we have 0 and 1 signal and combination of 0 and 1, so we want to have output 1, okay, what you should have. So as you learn in the digital electronics, okay, you have the gates, all right? The digital gates, okay, you have AND gate. So you know that this function, okay? So if it is an AND, then you know that it will becomes 1 when both of the inputs are 1, okay? And if it is OR gate, okay, if both of the gates are 0, then only it becomes 0, okay? And other than that, okay, it becomes 1, okay? And we have one more logic gates, which is a buffer, okay? So buffer meaning that we want to isolate or amplify the signal, meaning that we can control, we can amplify the signal, all right? Let's say from 3 volt, okay, we want to increase that, okay, it becomes 5, okay, we can use this buffer, okay? It actually, it does not change the logic level of the input, meaning that if it is 1, then it's still 1, okay? It just change the signal, okay? It's change the signal, but it does not change the logic level, okay? So remember that the function of the buffer, okay? Okay, and then we have inverter. Inverter is simple, so we just invert the signal. If it's 0, it becomes 1. Is 1, then becomes 0. Okay, and then exclusive OR, meaning that because OR it is giving you, okay, the results of all ones except for 0, 0 and 0 input, okay? But for exclusive OR, for if both of inputs are similar, then the results would be 0, okay? So here, if both are 0 or both are 1s, then the results become 0, okay? And we have the NaN function, all right? So the NaN function is inversion of N, okay? So whenever you have both same input, then it becomes 0. Other than that, it becomes 1, okay? NOR gates, okay, is actually inversion of OR, okay? So when both inputs are 0, then it becomes 1. Other than that, it becomes 0, okay? So as you learned before, as I mentioned, so you know that, okay? You look over here. What's the, if you want to get the carry and sum over here, okay, the sum column matches the output of the XOR function, okay, as you see that, okay, sum column, okay, you use the XOR gate, okay, mean that whenever you add, okay, whenever you add, you sum both of the inputs or outputs, it becomes always become the result of XOR, okay. So it only becomes 1, okay, when you add 1 with a 0, okay, not with 1 with 1, because you have a carry, right? So that becomes exclusive. And then the carry column, so is the N, okay, okay, because you see that whenever your output, okay, is, okay, You see that 0 times 0, it becomes 0. 0 times 1 still becomes 0. Unless it is 1 and 1. So 1 times 1, it becomes 1. So this is the replication of n. Okay. So because you want to get both addition of that, so you want to perform the addition. So you have the skirt signal, right? And you want to perform the addition. Okay. Then you need to make sure the signal go through this AND and XOR gate. Okay, then you will only obtain the results of the summation. So this is what we have in the arithmetic logic unit. Okay, ALU. Okay, as I mentioned previously. So we have the logic unit. So arithmetic means it involves the calculation. Okay, with the logic unit, then you get the results. Okay, all right. Okay, I stop here for today. All right, so because the other part of that will take longer time to complete. All right, so I stop here. So we'll meet again next week. Any question so far? No question? Okay, then let's finish here. Okay, so turn on your camera for me to take your attendance for today. Okay, so we will have one more session, online session next week. Okay, before we start meeting physically, week after that, right? And then we will see you for 2 to 3 weeks before we have our semester break. Okay, so you guys ready? Okay, let me count from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. All right, thank you everyone. Okay, so I see you again next week on Monday. By the way, I will give you exercise by I'll try to upload it tomorrow. Okay, so you will have it depends. I will look into the assignment first. So for now, I haven't set the due date. I will let you know the due date later during the on Monday. Okay. Okay. Stay safe. All right. Take care, everyone. Okay. See you next week. Okay. Bye bye.
Thank you,
Thank
Doctor.
you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.